Hi, everyone, and welcome to the NeuroNexus Podcast, where we take a deep dive with the researchers using our tools to push the fields of electrophysiology forward. For over 20 years, NeuroNexus has been a leading provider of silicon probes. In response to the evolving needs of the field, we've expanded into data acquisition systems, accessory instrumentation, and cutting-edge software, together supporting rigorous research featured in nearly 5,000 publications. In this show, we break down the science, the setup, and the real-world lab experiences that don't always make it into the publications. Whether you're a longtime NeuroNexus user or just getting started in electrophysiology, you'll find something useful, relatable, and inspiring in every conversation. So let's get into it. You guys are talking about probes. What are you talking about?
We are talking about doing semi-chronic recordings. So our typical approach is an acute recording where we put an electrode in, probes now, arrays, and typically 2 to 4 now. We'll put in simultaneously. But we put them in at the beginning of the day and we pull them out. We are talking about experiments to look at sensory motor associations, the formation of sensory motor associations in parietal cortex. And so what we want to do in an ideal setting is leave probes in and really measure ideally from the same neurons, or at least very local populations over the course of weeks of learning. And we're thinking about pulsation of the brain, rigidity of the probe, how and other factors like gliosis might be limiting our ability to record for long periods of time.
Yeah.
Naturally. Yeah. So we're thinking, neuropixels, or just synapse, I think, which is your solution for very high density recordings, and then just the silicone probes that we're already getting from you guys now.
Yep.
Yeah.
Okay. Now, can you educate me, because I'm not sure. So with neuropixels, what did they have in the way of non-human primate probes?
They have probes that are 40 millimeters long. So they just took their whole device. So their original NeuroPixel 1 probes, or whatever they called it, were like 10 millimeters long. And had something like 2,000 sites on them or something like that. For the non-human primate stuff, they just extended it to be 40 millimeters long, and those have 4,500 contacts. But you still can only record from banks of them at a time, obviously.
Yeah, which is definitely not what would be ideal.
I think they've got a workaround where you can select for subsets of channels across multiple banks.
No,
but
they're restricted to banks, I'm pretty sure. Given how it's wired, but
I see. This is it's talking maybe with. That's not what Jan said, but.
Oh, okay. My understanding is that they're in banks.
They are in banks, but there's some workarounds. Yeah, but it's still not very flexible.
Sure. I still know you're limited to 300 channels or something like that.
And then that's one of the advantages with the Synapse probe, is that you can record from all of the contacts at once, correct?
Yeah. How many contacts is on the Synapse? I don't remember.
It's a good question. I'm not entirely sure. I'm pretty new with the company.
Sure.
Yeah. So there is a version now for monkeys. With Synapse, I remember early on there was plans to have a monkey probe, a monkey compatible probe, but I haven't followed along.
Okay.
Does that actually exist yet or not?
I guess I haven't heard of anything, but also I'm very new with the company. And then you guys are using our vector probes, and so how are those working for you?
These work well for us. We have 3 different versions now that we use, or 3 or 4 versions. The first one we bought was customized. And so we rely very heavily on that for all of our neural recording experiments. That probe we designed for a very specific goal. We wanted to leverage high density recordings to record simultaneously from coding and non-coding populations of neurons as the monkeys are performing tasks. But we wanted to maintain isolation of single neurons. So So what we did was we designed an array that's made up of tetrodes, so that we could get strong, clean isolations from tetrode spike sorting, base spike sorting, and separate the tetrodes enough that we weren't really worried about spillover from one cluster of tetrodes to another. So we can record from spatially distributed populations of neurons, and at the same time get clean single unit isolation. So it was a nice balance of those two objectives of distributed neurons spanning coding and non-coding populations for a given stimulus.
Yeah, and then with those tetrodes, how many are there? I guess how many recording sites are there on the probes?
We have a 4 tetrode version and an 8 tetrode version. I don't think we use the 4 anymore.
No, we almost do everything out of 8. But when they were first designed, it was a 4 tetrode version, so it would have been 16 channels. And then we eventually went to 8 tetrodes, which was 32 channels, to span even more space. So an 8 tetrode probe at our configuration spans about 2 millimeters of cortex. So we can record from subpopulations across 2 millimeters of cortex. For tetrode probe is half that. So it just gave us the flexibility to record from more populations simultaneously.
Yeah, so we've been happy with that, quite happy with that. There used to be some quality control issues, but I think those have been mostly solved, or do we still send probes back?
No, I mean, you're new, so this might not mean anything, but you guys came out with another coding or a Z coding or something like that was better for the electrode contacts, and then we haven't had so much issue in terms of channels dying.
Yeah, so
time.
I wasn't referring to that, but yeah, that was another. I'm referring to like the silicone wasn't on the shaft.
Oh yeah, we haven't had any of those anymore.
No. Yeah, it's been a long time.
Yikes! Yeah, that would be a problem.
Yeah, when we first got them, I'm exaggerating, of course, but there was an obtuse angle between the shaft and the silicone occasionally, and so but they were good about it, and we would send them back. They would often ship us a probe before they even received the original one back, but that's been resolved now. They're all a single line.
Yeah.
The shaft and silicone, and so that works. With the edge arrays, they're not custom designed, right? That's out of the catalog.
No, I think it's out of the catalog.
Yeah. So we also so that's what we do for our neural recordings, but we also have experiments where we do microstimulation. And so this is I think one of the really nice things about the probes that you sell, which is that, so there we bought the edge arrays, which have 50 micron spacing, I think, and 16 channels.
We can get them at 16 and 32. We have both.
We 16 or 32 channel versions of that, and then what we do is we insert that into the tissue, into the brain parenchyma. We functionally characterize simultaneously units along that entire densely sampled shaft. And then what we do is we calculate measures of clustering along the probe so that we can identify individual channels where within a given spatial distance, the selectivity of all the units that you sample are most similar. And then we select stimulation channels based on those metrics in an attempt to just kind of improve the outcomes of those experiments.
Yeah, that's neat, being able to have the, I guess, fine control over where you're stimulating in response to the activity that you're seeing.
Yep. And we've known the field is known for 30 years that the effect sizes that you get behaviorally when you electrically stimulate at a single channel are very tightly determined by the strength of clustering around the stimulation site. And so this means that we have very few bad days on an electrical microstimulation experiment where you don't get any effect, and then you're left wondering, is that just because you didn't properly characterize the variance in selectivity around that site?
Yeah, I mean, as a comparison to what was done historically, you take a single channel probe, drive down, measure properties, drive a little bit further, measure properties, drive a little bit further, measure properties. If all three of those measurements are the same, you pull up to the middle and you're going to stimulate. But if any of those are different, then you just keep going down and doing that process, right? And so it's iterative, and maybe you don't guarantee to find what you're looking for.
Yeah.
Using your guys' probes, we can just penetrate to one depth, characterize all the spatial locations simultaneously, and then pick sites accordingly. So from an efficiency perspective, it is greatly increased by using linear arrays compared to the way things used to be done.
Yeah. And then the probe settles once. You don't have to. And then just the recordings are much more stable. It's no longer subjective. I think that's one of the things that I really like about that approach.
Whoa, what do you mean by that subjective? You're talking in terms of the activity into where you're going to be stimulating?
Yeah, just what does it mean to be similar? So as Ray just described, you move the probe up and down a little bit, within a few hundred microns. You measure selectivity. You move the probe, measure again, and you say, are these similar? Yes or no? Okay, this would be an okay place to stimulate. But that introduces a lot of room for subjectivity in what is similar, and you generally don't have a good way of quantifying that. You'd have to record, analyze, show, and you just don't see very quantitative comparisons of each of the test sites before that went into choosing the stimulation site.
Yeah. So being able to have that right there is really useful. Now, can you remind me, are you guys using our acquisition software, Lego, or are you guys using something different? What are y'all using?
We use Grapevine Ripple.
Oh, okay.
Yeah.
Why? What's nice about that? Tell me about it.
At the time when we built the system, it had the ability to do everything that we wanted to do in terms of spike channel counts, local field potential, signal acquisition, but then all the analog and digital channels that we need to simultaneously record what the monkey's doing, what the stimulation is being shown, so all these other parameters that we save in one big data set so that we can later analyze what happened moment by moment. We just needed that kind of a configuration to do that. And so I don't know, 10 years ago now, when we did some of that, that was a nice solution for that.
Yeah.
And so they have head stages that interface with your probes. And so then that's been our setup.
Yeah. The two other points to add are they have a very good control for electrical microstimulation. And then the other at the time they were at a really good price point for what you got in terms of 100, and we use the Scout. We have about a couple of Scouts systems, so those have 128 channel counts. You can stimulate on 32. On a head stage has 32. Yeah, so you have a lot of flexibility in terms of which channel you're stimulating when you pair it with a probe like the ones that we buy from you. And they have fast reset between stim and record. So you're really able to look. You have good temporal control for data acquisition and microstimulation.
Yeah, it sounds like it's checking all the boxes that you would want it to. So that's awesome. So now, can you tell me, when did you first start using our probes, the vector probes?
2016, end of 2015, early 2016.
Or a year later.
Is it a year later?
Because I know T United a bunch of single channel stuff, and then we moved in. But I don't remember when you first had conversations. I don't know about that timeline.
You did the first one like a week before we submitted the first R1.
We used the tetrode?
Yeah. With a tetrode.
Oh, okay. Because I still cut my teeth on tungsten wires.
Yeah, but that's because I didn't trust laminar probes at the time.
Oh, yeah, probably about that range.
Yeah, maybe end of 2016.
Okay.
So somewhere in 2016.
What do you mean you didn't trust laminar probes at that time?
Oh, it was new. I think I bought 3 or 4 of these from you spent some time doing the design on what I thought would be a good probe, bought 3 or 4 from you, and then but needed to test them.
Of course.
Yeah. So had not established, a working relationship. Didn't know about quality control. What kind of signal isolations we would get, whether or not the silicone would just the contacts would become dead, very quickly, what kind of resistance they had, impedance they had initially, how long they would last, whether or not the probe itself was durable, would the glue holding the silicone to the shaft flake off. There's lots
so
of
many
unknowns.
things. Yeah, so many things to consider. So when you were implementing them into your lab for the first time, were there things that came up that you didn't necessarily anticipate that you kind of had to work through that now are like second nature? Anyone that's coming through your lab, you can tell them like, hey, this isn't super intuitive, but this is how it's going to be.
I think the big one was just dealing with the delicate nature of the silicone where it's attaching to the shaft. And so we 3D printed, we designed and 3D printed some devices to help backload the probes.
So that's really helpful.
Yeah, I've got there's a few people in the lab that have very steady and very steady hands, and others that are not so careful, maybe a little more shaky. And so we had a student around 2017, 2018 that broke maybe 3 or 4 $2,500 probes in the course
oh my gosh
of a week or two.
Oh no.
So that that was a moment where we realized that there's some things that need to be worked out, but it's just a matter of how to handle the probe and make sure you're delicately loading it into the guide tube. We there's some related developments to that. For a given monkey, there might be, depending on where you're recording from, within an area or across areas, you might need a few different guide tube lengths. And so rather than pulling probes out and reloading them on a daily basis, we just built a multiple guide tubes, so a fixed guide tube length, each with a probe permanently loaded into it until that probe goes out completely. And so then we just, that was a strategy change from single electrodes where you would have, a handful of guide tubes, and you knew based on your mapping of the areas what size guide tube you would need, and you would load it with your electrode on a daily basis, to having an array of guide tubes preloaded and sitting in enzyme to keep them clean. And
it's like a fundamental change in technology. So with it came just a change in mindset and approach from the way things were done in the olden days.
Yeah. And so now with the acute application of the probes, now you guys are reusing these probes, correct?
Yeah.
How many times do you think that you can reinsert the vector probe?
We get to upwards of a couple months. So a couple months would mean, I don't know, over 30 penetrations, maybe 36 penetrations before contacts wear out or things like that. For the linear arrays that we've been using for microstim, because we're injecting current, there's much more of a frequent ion exchange across those. So we burn channels out more frequently because you're stimulating and injecting current into the tissue through those channels. And so you get dead channels that way. But from ones
those are single channels that die. Right. So you can still use the probe for a little while. You just lose a channel or two.
Right. But once you have enough dead ones in an area, then it's kind of hard to use the probe because you've now lost your spatial ability to
sample.
But for the ones that we just, I'll say, passively record from, or the tetrodes that we use, those rarely die out over time. It's usually just mechanical failures that is the end of the life of that probe.
Yeah, what do you mean by mechanical failures? What does that look like?
Either someone still mishandles them and breaks them, or sometimes where the support tube on these probes interfaces with the silicone, there's a adhesive or something that interfaces that point and protects the internal electronics from fluid and other things like that. And so sometimes that part will degrade or pull off over repeated penetration times, and then the signals all get grounded together that way when fluid gets introduced into other parts of the system. But it's really just a mechanical property of just the lifespan and repeating some process over and over. But from an electrical recording point of view, we've had channels last a long time, especially since the new coding.
Z coding.
Z coding. Yeah, that's awesome.
Years ago.
So then when one of the contacts does go out, how can you notice that? Say it's like channel 16, do you start seeing a funny looking signal? Or I guess what would be the key markers to know that a channel is going out? Are you looking at impedance? What?
Yeah, we can use impedance. The Ripple Grapevine Scout system offers a way to try to measure the impedance of the channels in real time per se by I think injecting a little bit of current. So we'll notice an impedance change, but more than anything, the signal will just go away. We've now lost the ability to record spikes or action potentials from individual neurons, whereas neighboring sites are picking up activity. You won't see that channel, in your example, channel 16, will just be, as we call it, dead because it's not picking anything up.
We have seen a couple times, at least once, where two channels will be coupled. I don't know if that was on a fresh probe or if that was something that happened mechanically later that they got coupled. But there's been a couple of funny instances where, you've got two tetrodes that are separated by 600 microns or 900 microns, something like this, and within each of those cluster of 4, there will be a single channel that is that's exactly the same. That's a kind of a funny thing that has happened, but that's rare. That's exceedingly rare.
Yeah.
And stands out because that just you shouldn't have a cross correlation of 1 on the hundreds of microns scale.
Yeah, that is kind of funny. So I was wondering if you could talk a little bit about the signal quality, I guess like signal to noise within NeuroNexus's vector probes.
Yeah, I haven't calculated like SNR as like a number, but I think, our strategy, it really comes down to the setup in the room itself, and the ability to try to exclude all environmental noise, right? We're in a busy building with lots of electrical components, right? We're not one isolated room in the middle of nowhere. So trying to track down any possible signals of noise and ground loops and this black magic that occurs through electricity, and overcoming all of that has been a lot of effort. But once you do so, you get incredible signal quality.
Yeah.
But yeah, I mean, the activity of individual neurons stands out many times, many magnitudes higher than what the background noise is, right? So we get a really good signal to noise with your guys' probes, and I think we always have.
Yeah.
Yeah. At some point, I think we did some calculation, but it was 8 years ago, and it was, as Ray said, we've not had any issues. The isolations are strong. The signal to noise is far beyond what we need to get clean isolations, especially with tetrodes. So
nice. Now, I don't know if you guys have seen, or maybe you do have them, but are fusion style vector probes where it's 2 128 channel electrodes that are glued together, and so you get 256 channels, which is kind of cool. But I guess, is that something that you guys would be interested in?
By fusion, you mean you kind of glue them front to back, right?
Yep. Or I guess, do you see any potential issues with that? It's a newer thing for us, and so just trying to gauge what your thoughts would be.
Initial thoughts to me right now are comparing gains versus tissue damage. So you want to try to minimize the footprint that you're pushing through cortex, so that you can hopefully come back to that area and or similar area and continue to record from populations, and that you haven't, through trauma or mechanical stress or things like that, destroyed or damaged a lot of that tissue. And so having a smaller footprint in that area is beneficial. And, and given our tetrode configuration, it's kind of like having 4 ears, or the way that an owl localizes sound, right? And so you can pick out individual features better. So I'm not quite sure if a neuron fires behind my probe, I'm still probably going to capture that electrical activity on the front of the probe. The signal may be stronger if I have channels facing the other way, but I'm sure that I'm still capturing that activity, because that activity is more spherical than it is like a cone of sound or something like that.
Yeah.
So it would be a way to increase the density in which you have channels per unit distance, but you'd also, obviously, in this kind of way of fusing them together, you're gonna have to increase the thickness of that probe.
Yep, footprint is definitely a little bit bigger.
It also depends on what the configuration of the contacts are,
and
whether or not that gives you. So, the way that having multiple contacts helps you is that the relative distances from a given neuron are to the contacts is different, and so you have multiple perspectives on the activity. And so, I think it's more beneficial to have staggering like that side by side and vertically offset than it would be to, say, have two contacts that are just back to back. But it depends on the thickness of the probe and the thickness of the glue, because if you're adding 30 to 50 microns distance, then that offset in width of the probe would be useful. Especially for capturing units that are further away. So it could help. Yeah.
Cool. Interesting. Thanks for your thoughts on that. So then I guess farther down the line after data acquisition, and I was reading some of your guys' work, but as far as the signal processing and subsequent analysis, what are you guys doing for that?
All the spiking data that gets saved by our Grapevine Scout system, we run spike sorting, either manual spike sorting or semi-automated spike sorting with some of these other algorithms that are coming out, like Kilosort. And then in most of the work that we've done so far and are continuing to do, are interested in looking at single unit responses and properties. So the goal there is to take the spikes, perform clustering, and isolate into activity of individual neurons to look at functional properties related to animals' behavior and things like that.
And then are you looking at the spiking in response to the stimulation? So kind of like that time lock, almost like a time trial for the stimulations?
But to visual stimulation.
Yeah, but it's tricky to do that when you're injecting current, because you can't record and inject something at the same time, and it creates noise in the system. So there, we're more looking at behavioral responses as a function of injecting something like that. But while the animal's engaged in a discrimination task or performing some kind of behavior, that kind of stimulation is what we're counting spikes or action potentials or characterizing functional properties relative to.
And correlations across neurons.
Oh, yeah, of course.
Yeah.
Okay. And then are you guys doing anything with local field potentials in addition to single unit spikes?
We do, not for every project, but we do have one project where we are relating local field potential activity to spiking activity and behavior of the monkey. So there we're interested in the phase locking activity in the beta frequency band in the local field potential across areas in which we're recording simultaneously, as well as the occurrence of phase resets based on cognitive demands of the monkey on the monkey in the tasks. And so there we do look at the local field potential channels.
Neat.
Yeah, in the Ripple file.
Very cool, very cool. So we kind of touched on it a little bit earlier, but you said that you first got our probes close to 10 years ago. And so I'm curious on your perspective of how the in vivo electrophysiology field has kind of evolved, because I feel like thinking to slice electrophysiology and then working its way up to now, we're going from like single channel activity to thousands of neurons at one time. I just kind of am curious about your perspective on that.
I think it's aligned. It's pretty well with where we were anticipating the field to go. In the past, you had just a single electrode and you were recording from one, maybe two. On a rare occasion, you would get three isolatable neurons on that electrode at a given time. And so there is a tendency to handpick neurons based on the properties that you were evaluating based on some initial screens. And so it was a much more subjective view of how the system works. Limited in that it's only looking at activity of a single neuron at a time. Limited in that there is a probably quite natural bias to record from neurons that are responding in ways that you can have a straightforward interpretation. With probes like the ones that we've been using and now with even much higher densities, you record everything simultaneously. So it gives a different perspective. You tap into not just coding and non-coding populations in the sense of that there are features of the stimuli that drive some neurons but not other neurons. But you also get potentially coding neurons that are responding in ways to your stimuli that you wouldn't have anticipated if you were just recording from large pyramidal neurons that behave in the ways that you were able to quickly online while recording from the neuron make sense of what was happening. So I think it opens up the field in the sense that we have a broader perspective of how neural systems represent information, transform sensory signals into decision variables, and ultimately motor responses. It makes it a little harder to impose our preconceptions of how the brain works onto our data when you record everything that's there to be recorded.
Mm-hmm. Yeah. With the mass amount of data that is available to us using these methods, the analysis that we're using, that has to be super, super tight and really rigorous. And so how do you think that you've been able to implement that as these data sets have just continued to grow? How do you think that you've been able to make your analysis like as tight as possible?
It's challenging if you want to maintain a single neuron perspective where you're isolating individual neurons, just because the amount of data is so large. You can facilitate the process with semi-automated sorters, but they only work so well. There is a large time commitment to data curation and making sure that the isolations are clean. So that's one part of it when you're looking at what's happening at the single neuron level. These probably are less of a concern when you're looking at population level analyses using any number of dimensionality reduction techniques, because it's okay if you're working with multi-unit activity, you're compressing the data down anyways. And so there you have different challenges. The assumptions of the analyses can potentially get you into a lot of trouble because in many cases they're imposing structure on the data, and so there you just really want to make sure that the structures that's being imposed on the data aren't artificially creating results. There I think what you really have to do is just simulations, and you build artificial populations of neurons where you know everything that they're doing because you've defined the processes, and then you just have to be very careful with evaluating the rigor and the interpretation of the analysis results.
Yeah, I think that is a really smart thing to do. I did that in my PhD. Is I generated this data set where I knew exactly what every single neuron was doing and how the analyses should play out. So then when I was coming up with my analysis pipeline, if it didn't equate to that, I knew that something was going on that was funny with it. And so, yeah, I think that is a really, really good and important thing to do to optimize the analysis.
Look, you're right. Just because the function executes doesn't mean it's doing what you think it's doing.
Yep.
Yeah, so
Exactly.
Surrogate data sets take you a long way in validating your methods.
Mm-hmm. Yeah. So with everything that's coming down this pipeline, is there anything in particular that you and your lab are really excited about? Any new findings, any new work, any new methods, anything that's got you really excited?
What's exciting you?
So with doing high density recordings, my interests from a development perspective are trying to look at recording neural activity across learning. So in the past, if you had single channels, that'd be very hard to do day by day, acute penetrations, things like that in non-human primates. And so now, as we have more technology to even collect this larger data set, but then also have the computational tools to hopefully track populations or subpopulations of neurons across time. Now we can look at the neural dynamics instead of just a day by day or a stimulus by stimulus, but see how some of these things change while an animal learns how to do a task or is becoming familiar with a new stimulus or a new paradigm and things like that. And so leveraging, so that's more like a scientific interest, leveraging that technology. But from a technology perspective, it'd be kind of how we started this conversation about trying to do, chronic sorts of recordings and things like that, and having technology support that use case for instance, right? So rigidity is a big problem when you have a brain that pulsates every time you inhale, or blood vessels take blood through them, things like that. And so, being more like the tissue per se, and so that you move with the tissue instead of asking the tissue to move around you, I think would be an interesting future perspective to continue this growth and development.
Okay. And now when you're talking about a chronic recording, you're talking about putting the probe in and leaving it in there for weeks, months.
So some extended period of time.
Yeah. And then being able to track the exact same neuron across an animal learning a task. Yeah, that would be super powerful.
World, right? That'd be a perfect world if you could track the exact same neuron. The feasibility, that's quite challenging, but would be ultimately the goal. I mean, you can say that you do that with Utah arrays or something like a Utah array, right? Where those are permanently implanted. But the nice thing about using probes in this case is the fine-tunement or the adjustability, or that it's on a penetration that can be retracted. And more so for us, it allows us to reach deep cortical structures, right? With the Utah array, you're really limited to surface penetrations and things like that. So if we want to get deep inside some sulcus in the parietal cortex, that technology is no longer available for us to try to look at chronic sorts of recordings. So this kind of technology would help support those endeavors to parts of the brain that aren't accessed directly underneath the skull.
Yeah, okay. I think it comes down to time scales, and when in times past, when you had a single electrode in the brain, you had just you had a spatially limited snapshot and a temporally limited snapshot. You knew what one neuron was doing over the course of a couple of hours. Even now, with very high density recordings, electrophysiological recordings with many contexts, it's still just a snapshot. You can capture the dynamics of what cortical populations or neural populations, so cortical or subcortical, just neural populations in general. You can capture what the dynamics of that population is doing, but it's still only over a very short period of time. It's still a snapshot of a couple hours in the animal's life, and what you really want to eventually be able to do is to record those dynamics, not just over hours, but over days and weeks and months. And so it's a matter of time scale and the time over which you can capture population level dynamics. And that's really what where we're thinking about going next in terms of understanding neuroplasticity.
Yeah. And now I've never done chronic recordings in non-human primates, but is that something, can you do that with our probes, or our probes are too fragile, too rigid, talking about the pulsating of the brain? What do you guys think about that?
Yeah, we haven't
tried.
We haven't done it yet.
Okay.
But we're in the process of doing so.
Cool.
From a footprint perspective, what I like about, well, the flexibility that you guys give us is that for all of our acute recordings, we have some silicone part that has all of our channels, and then some support shaft, which then we can hold and manipulate to drive to the parts of the brain that we're interested in. And so we can use that setup to do lots of acute recordings, and that's all the research that you've read from our lab previously is done using that technique. But you guys also have what you call a chronic package, where you can cut that support tube at any length that I need it to be cut at, and then you just give me a ribbon cable for the rest of it versus having that all embedded inside a support tube. And so now I can have the exact same recording capabilities in a much smaller footprint that I can package to create a system for doing chronic recordings that doesn't have some long lever arm, right, coming off of the animal's head or their implant or something like that. And so from that perspective, we have a couple of your chronic probes that we're using to develop the procedures and techniques that we need to do these chronic recordings.
Okay, that's awesome.
We're actively moving that way.
How is that going? I guess optimization of that.
Good. It's all about just, like Ari was mentioning, when you move from single channels that you place in a guide tube every day to these silicone probes that are much more fragile, it's all about how can you create a robust procedure that is tolerant to different users and loading strategies and things like that, so that it's repeatable, but also easy, and you're not sweating bullets for a couple hours trying to load this one probe before you actually do the experiment that you need to, right? So we're kind of in the support phase where we're developing all the support materials we need to help us be successful in these endeavors.
Yeah. Wow, that's awesome that you guys are doing that. Is there really a way to not be sweating bullets when you're working with a non-human primate and a $1,000 probe that's super fragile?
1,000? Aren't they more like 25?
Yeah, they're more like 2,500 or 3,000.
3,000.
Yeah.
The ones that we designed.
Yeah. So no, it's just it just comes with the territory.
Is there somebody you're charging 1,000 for these?
Yeah.
If you are, I want that discount.
It's not the right.
I'll have my people talk to your people. We'll work something out. Yeah, but I could imagine that would be a really, I don't know, high stress surgery, and even the prep for it, dealing with that type of equipment. But I think that's awesome that you guys are working to come up with a chronic system that you can work and that it can be as streamlined as, like you said, easy as possible. I think that's really going to be beneficial to you and probably the field to be able to do these chronic types of recordings.
Yeah, the big question is whether or not we'll be able to maintain isolation, or will there be gliosis and you lose and the impedance goes too high to record anything, or if there's shearing forces as the brain's moving against the electrode that are killing all the cells. So these are empirical questions that we're just going to have to see.
Yeah. Deal with them as they come up. And then I guess my final question for you guys is, if there was anyone that is interested in kind of getting into this field, maybe it's a PI that's starting their own lab, or like an undergraduate student that is thinking, hey, this is really cool, something that I would want to get into. Do you guys have any advice for people at different stages in their career to help them best succeed in non-human primate in vivo electrophysiology?
That's a good question.
I think if you want to solve human problems, you need to be working with a primate model at some point. I think it's a worthwhile endeavor for somebody that's not working with monkeys currently to move into, if their ambition really is to solve problems related to executive control or complex sensory motor learning, ensuring that the results, the neurophysiological results map onto something relevant to humans. And so it's to break into that space, though, it's essential to find strong collaborators who have the expertise, and then it's just a matter of spending some time in a lab and picking up some techniques that you can bring back home with you. But it's challenging. There are many ways that an experiment with a monkey can break down, and so you need to be ready to deal with all of those, and that's something that takes experience to gain that ability. But it's certainly worthwhile, and the kinds of questions you can ask, there's just no other model system to work with that gives you such deep insight into neural systems and their relationships to behavior.
And I think from a technology standpoint, like you guys do, you develop really high quality probes that give you really good signal to noise, that you now have, your Radian software, your acquisition system. So it's like a one box plug and play kind of a system. So for people looking to get into that space, that technology is all solved by you guys, right? That's not a lot of development that has to happen at the bench anymore, right? But as to piggyback what Ari was saying, to find collaborators or someone who does have a setup, to get the experience of, okay, I have a system, but how can I use it, right? Just because your probe can give me good signal to noise, if I'm in a noisy, rich environment, then it doesn't matter how good your probe is, right? I need on my end to shield or control for some of that. And so I think that's where the experience really comes in, is learning how to use effectively systems, and these really cool systems built by companies like you guys.
I definitely agree. Having a strong collaborative network that's priceless. I mean, you can have the best tools, but being able to have someone that can inform you on best practices that's very, very important.
Yeah. You have to be able to work with the animals. You have to be able to design experiments that are amenable to those animals.
Yeah. Neat. Awesome. Well, thank you guys so much. I don't want to take up any more of your time. You've been super informative, and I've really enjoyed chatting with you. I guess I do have one last question. What is that gorgeous looking piece of art in the background? What is that?
That is a geometric pattern consisting of elephants, peacocks. I think there's some other animal in there. Leaves and other geometric shapes. It's a print that I picked up in India sometime back. Yeah.
Where in India?
I think I picked that up in Delhi.
Okay.
Delhi or Hyderabad. Quite some time ago, but the inks are all natural inks from plant-based inks, and then the paper you see, it's not crisp white. It's kind of got a brownish tinge to it. I'm not sure if you can get that level of detail through Zoom, but that's because they use cow dung as a natural preservative way to deal with infestations of bugs. Somehow it keeps them out of the paper and has some preservative properties. So it's cool, and it's pretty because it's kind of looks a little bit. It's a nice geometric pattern with lots of interesting symmetries. Circular and mirror symmetries. It's fun.
Yeah. I spent some time in India this summer, and I saw that, and I'm like, that looks Indian. Cool. Awesome. Well, again, thank you guys so much. I hope that you enjoy the rest of your day. And yeah, we'll be in touch.
Sounds great, Rosie.
Nice
meeting you. All right.
Thanks,
Look
guys.
forward to seeing what you put together.
Yeah. All right, everyone. That is the end of today's episode. Thank you so much for tuning in. We've linked today's guest in the show notes, so please go check them out. They're doing truly incredible work. You'll also find a list of the NeuroNexus products they used in their research, which we hope is helpful whether you're setting up a lab or optimizing your current workflow. This show wouldn't be nearly as interesting without the researchers who join us. If you're using NeuroNexus products and want to showcase your work, we'd love to feature you through a full episode, a short spotlight, or simply sharing your research with the community. You'll find a showcase submission form link below, so go ahead and fill that out. If you found this episode interesting, make sure you're subscribed so you never miss a conversation. We're actively building connections within the electrophysiology community, so come join us on LinkedIn, X, Blue Sky, Reddit, and Instagram. This podcast is powered by NeuroNexus Technologies, advancing electrophysiology at every step. We'll see you next time.